unlocking the mysteries of atmospheric blocking systems, impacts, types, and detection methods. Understanding and accurately predicting extreme weather events is of paramount importance to society due to the far-reaching impacts they can have. One fascinating aspect of weather dynamics that plays a crucial role in this endeavor is the phenomenon known as blocking systems. These are long-lasting, quasi-stationary, self-sustaining weather patterns that frequently occur in specific regions and significantly affect our ability to forecast extreme weather events. Let's delve into the key aspects of blocking systems and their relevance. Number 1. Influential factors. Blocking systems have a profound influence on the predictability of weather extremes. A critical factor in understanding these systems is the relationship between surface-level weather patterns and upper-level blocking anomalies. This relationship plays a pivotal role in the development of extreme weather events. Number 2. Seasonal variations. The impact of blocking systems varies with the seasons. In summer, they contribute to the formation of heat waves and droughts by causing large-scale subsidence, which results in clear skies and sustained warming of the Earth's surface. In contrast, during the winter, cold waves are often observed downstream or to the south of blocking systems, driven by the advection of cold air from higher latitudes. Number 3. Alteration of storm tracks. Blocking systems can also influence the typical paths of storms, leading to shifts in storm tracks. These alterations can, in turn, affect the occurrence of wind and precipitation anomalies, adding complexity to the weather patterns. Number 4. Compound weather events. One striking characteristic of blocking systems is their propensity to coincide with compound weather events. These are situations where multiple extreme weather phenomena occur simultaneously or in close succession, making them particularly challenging to predict and manage. Number 5. Climate change connection. In the context of climate change, it's essential to assess how blocking systems may evolve and how they are linked to extreme events. Understanding these connections is critical for adapting to changing climate patterns. Number 6. Diverse synoptic structures. Although there is a common thread in the characteristics of blocking systems, there is no one-size-fits-all definition. These systems exhibit rich diversity in their synoptic structure, making them fascinating subjects of study.
Atmospheric scientists have been studying blocking since the 1950s, so a little over 70 years. However, the relationships between extreme weather events and blocking are generally not fully understood yet, and they're still being explored. The reason for this is that the dynamics of blocking systems are complex, and they cover a wide range of spatial and temporal scales. A better understanding of dynamics through more and better observations would have a positive effect on capturing blocking systems and their interactions in numerical models. At present, the representation of blocking in numerical weather and climate models has several weaknesses regarding how often it occurs, how intense the phenomenon can be, and how persistent it can be. The life cycle of blocking systems, the onset, the decay, are still considered challenging for numerical models. And due to the fact that blocking decay is difficult to predict, the duration of the event itself is often incorrectly predicted. What that means is that the inaccuracies in predicting the decay of the blocking system can influence the predictability of the decay of a weather extreme, whether that might be a heat wave, a drought, or even a cyclone that might exist downstream of the blocking system. Currently, the connection between atmospheric blocking and the predictability of wind extremes. At present, the connection between atmospheric blocking and the predictability of wind extremes or intense precipitation is still understudied. Therefore, we need more research in order to quantify the potential of these relations, something that will be important for weather forecasting and climate projections.
Types of blocking systems. Researchers have identified various types of blocking systems. Some examples include Rex or dipole blocks. These involve an anticyclone positioned poleward of a cyclone and are closely associated with the breaking of atmospheric Rossby waves, resulting in a meridional flow pattern. Omega blocks. These systems feature a substantial anticyclone flanked by an upstream and downstream cyclone, creating an omega-shaped flow pattern. Amplified ridges. In some cases, amplified ridges with no closed contours can disrupt the zonal flow, leading to a dominating meridional flow component, especially in the summer and at lower latitudes.
Generally, any of the three types of blocking can be associated with Mediterranean cyclones. Various types of blocking can be found in the Euro-Atlantic region, and they can cause a deflection of the typical storm track towards the Mediterranean, or even induce cyclogenesis downstream in the Mediterranean itself. An amplified ridge, often accompanied by a trough, is perhaps considered to be the most commonly found type of blocking over the North Atlantic and European region, causing low pressure systems, cyclones, to either form or to intensify in the Mediterranean. But it's important to note that the specific effects of an amplified ridge on a Mediterranean cyclone can vary depending on the exact positioning and characteristics of the ridge, as well as the overall atmospheric circulation patterns that are happening at the time. For example, storm tracks in the Mediterranean can be found when there is an amplified ridge over the central Atlantic, or when there is a ridge in the eastern North Atlantic Scandinavian region, accompanied by a trough over Europe. Another example can be a ridge over Europe, accompanied by an upstream cyclonically overturning trough and a downstream anticyclonically overturning trough, essentially forming what is known as an omega block, which can slow down or stall the movement of these cyclones. And lastly, for Rex blocks, we know that they can alter the tracks of Mediterranean cyclones by forcing them to take more convoluted or unusual routes. We are currently trying to understand which types of blocking are important for downstream cyclones in the Mediterranean, in addition to why and how.
As we continue to unravel the intricacies of blocking systems, researchers are working to bridge knowledge gaps and provide insights into the future of weather prediction. This research is essential for enhancing our ability to forecast extreme weather events and adapt to the changing dynamics of our climate. To better understand and identify blocking systems in our atmosphere, scientists employ various methods and criteria. These techniques play a crucial role in pinpointing these long-lasting anomalies, which are fundamental to weather patterns. Let's explore some of the approaches used by researchers. Potential vorticity anomaly. One approach is to look for anomalies in potential vorticity, specifically at the 320K level. This method, as outlined by Schwiertz and a team of researchers in 2004, involves identifying blocking through the presence of a negative potential vorticity anomaly. This anomaly serves as a key indicator of blocking events. Meridional gradient reversal. Another way to detect blocking is by examining the reversal in meridional gradients and atmospheric properties. For instance, changes in the 500 hectopascal geopotential height, as proposed by Tibaldi and Molteni in 1990 and Scherer and a team of researchers in 2006, can be indicative of blocking events. This method involves monitoring shifts in the height of pressure surfaces at this level. Two-dimensional patterns. Some indices provide a more comprehensive view of blocking by presenting it as a two-dimensional structure. As seen in the work of Masato and a team of researchers in 2013, these indices offer a more detailed representation of blocking patterns, allowing researchers to gain insights into their spatial characteristics. Duration and extent criteria. In certain studies, researchers consider additional factors like the duration of blocking events, by recording the number of blocked days, and the extent of blocking systems. These spatial and temporal criteria, as explored by Barnes and a team of researchers in 2012, help in distinguishing the scope and persistence of blocking phenomena. It's worth noting that the choice of method and criteria may vary depending on the specific research goals and regional characteristics being studied. By employing these diverse approaches, scientists can effectively identify and analyze blocking systems, contributing to a deeper understanding of their role in shaping our weather and climate.
of climate change due to the connection they have with weather extremes such as heat waves, droughts, or heavy rainfall. These extremes can have severe consequences for ecosystems, infrastructure, and of course, human populations. And one way is by affecting agricultural productivity, which can result in destruction of crops and subsequent changes in food prices and food security. In addition, prolonged heat waves, which can be exacerbated by blocking, can cause heat-related illnesses and, of course, even fatalities, while heavy rainfall and flooding can cause waterborne diseases and other health hazards. Potential changes in weather extremes due to the global warming increase the necessity for better understanding and therefore better forecasting and risk assessment. And this improved forecasting and monitoring of these events can help communities prepare for and respond to extreme weather events, reducing their impacts. When it comes to climate change, blocking has often been a cause of concern, and that is partly because blocking frequency has been poorly simulated by climate models and even by numerical weather prediction models in medium-range forecasts. From studies, we know that the Euro-Atlantic winter blocking frequencies are projected to decrease on the western side, but increase on the eastern side. That suggests a shift towards the east of blocking activity. And for summer blocking frequencies, a few studies have reported a possible poleward shift, essentially leading to a decrease in blocking frequency in the mid-latitudes and an increase in higher latitudes. However, results are sensitive to the detection methods of blocking, and therefore they're highly uncertain. But overall, blocking is more likely to continue being a source of concern for the rest of the century, and that is primarily due to the connection of heat waves and droughts.